The desert snail is stranded on a bare limestone slab as the morning sun begins heating the rock beneath its single muscular foot. There is no shade within reach, no puddle hidden under a leaf, and no rain forecast for months. By noon, the stone may be hot enough to burn exposed tissue, yet this snail could remain here for 100 days and survive. At first glance, that sounds impossible. A snail's body is soft, wet, and constantly at risk of losing water. Place one on a dry kitchen counter and it immediately begins searching for shelter, leaving a silver trail behind it. Every centimeter of that trail costs moisture. In a desert, moisture is more valuable than food, and movement itself can become a fatal expense. So how can an animal that appears designed for a damp garden live among sun-baked rocks? The answer is not simply that it tolerates thirst. A desert snail survives by changing its behavior, sealing its shell, lowering its metabolism, choosing its position with surprising precision, and waiting in a condition that sits somewhere between deep sleep and suspended life. But one overlooked detail determines whether that sealed shell becomes a refuge or a tiny oven. First, what exactly threatens the snail during those 100 days? Heat seems like the obvious answer, but dehydration is usually the more immediate danger. A snail breathes through an opening connected to a lung-like cavity, and much of its body surface must remain moist for normal movement and gas exchange. Its skin is closer to a wet sponge than to the waterproof hide of a lizard. The snail also moves by sending waves of muscular contractions along its foot. Mucus reduces friction between that foot and the ground, allowing the animal to glide over gravel, thorns, and sharp limestone. Useful on a cool night, expensive during a drought. Producing a shining road behind your body is a terrible bargain when the nearest rainfall may be 3 months away. A human carries most body water behind layers of skin. A snail exposes a broad, damp foot every time it travels. Even resting with its body withdrawn does not completely solve the problem, because air can still circulate through the shell opening. Hot, dry wind pulls water vapor away, just as moving air dries a wet shirt faster than still air. Yet the shell is more than armor. It is a portable chamber whose entrance can be closed. When conditions deteriorate, the snail retracts its head, tentacles, and foot, then secretes a layer of mucus across the shell opening. That mucus dries into a thin membrane called an epiphram. Think of it as a temporary door built from the snail's own secretions. It is not a solid stone wall. It can contain tiny pores that permit limited gas exchange, but it sharply reduces airflow and slows evaporation. Behind that pale seal, the animal keeps a pocket of humid air around its body instead of exposing wet tissue to the desert wind. Some snails produce more than one barrier. They withdraw deeper into the spiral and build additional membranes, leaving insulating air spaces between them. Each partition makes the route for escaping water longer. The animal has effectively placed several closed doors between its body and the outside world. But sealing the entrance creates another problem. The snail is still alive. Its cells still require energy, oxygen must still reach tissues, and waste products cannot accumulate without limit. A sealed animal burning fuel at its ordinary rate would consume its reserves and poison its shelter long before the first cloud appeared. That is why the next transformation matters. During prolonged heat and drought, the snail enters aestivation, a dormant state used to endure hostile warm conditions. Hibernation helps an animal cross a cold winter. Aestivation helps it cross a hot, dry season. From outside, both can look like sleep, but inside the body, carefully coordinated changes are taking place. The heart slows. Muscular activity nearly disappears. Digestion stops because there is no meal to process. The snail suppresses its metabolic rate, reducing how quickly stored fuel is consumed and how much oxygen it needs. It is like closing an entire office building for the weekend instead of leaving every light, elevator, and computer running. This is the first major reason 100 days is possible. The snail is not living 100 ordinary days without drinking. It is stretching a limited reserve by making each hour extraordinarily cheap. Fat and stored carbohydrates provide energy, while biochemical adjustments help cells tolerate the changing concentration of body fluids. The animal must also manage waste. Breaking down proteins can produce nitrogenous compounds that require water to remove. During dormancy, many land snails rely more heavily on fuels that create fewer costly waste problems, and they can store certain waste products until activity resumes. Nothing is free, but the biological bill is postponed. The sun remains the most relentless threat. A membrane can slow dehydration, but it cannot stop a dark rock from absorbing radiation. On an exposed desert surface, ground temperatures may rise far above the surrounding air. A snail sealed directly against that surface risks being heated from below while sunlight strikes from above. The solution begins before dormancy. A desert snail does not simply stop wherever exhaustion catches it. During cooler hours, often at night or after brief moisture, it searches for a suitable resting site. It avoids heat-absorbing dark rocks, choosing instead to gather directly on a bare, pale limestone face. Surface matters. By choosing a pale limestone slab, the animal escapes direct contact with scorching dark soil that absorbs radiation. Reflectivity matters too. The light stone remains slightly cooler than the surrounding earth only centimeters away. Orientation can determine how intensely sunlight strikes the shell and whether the afternoon heat directly bakes the opening. Then there is color. Several desert snails have pale shells that reflect more solar radiation than dark shells. Consider Sphincterochyla boissieri, a light-colored land snail found in arid parts of the Middle East, including the Negev region. Against chalky stone, its shell can resemble a small bleached pebble. That appearance helps with camouflage, but it also changes the snail's heat balance. A dark shell absorbs more incoming energy. A pale shell reflects a larger share before that energy becomes heat. The difference does not make the snail immune to summer, but when survival depends on keeping tissue below lethal temperatures, even a modest reduction matters. And here the shell's shape joins the defense. The living body occupies only part of the internal space when deeply withdrawn. Air trapped inside the remaining chamber is a poor conductor of heat compared with wet tissue or stone. The shell and its internal airspace create insulation, while the epiphram limits the exchange of dry outside air. The snail has turned its home into a desert flask. The armor defending against the sun demands a heavy price. The shell itself requires immense amounts of calcium, and desert landscapes do not distribute this mineral evenly. The bare limestone slab provides abundant material for building and repairing a shell, but constructing that thick fortress costs massive amounts of energy, pushing the animal closer to exhaustion before the drought even begins. Starvation is the silent killer threatening the lockdown. During brief active periods, desert snails graze frantically on algae, lichens, fungi, and the thin films of growth that appear after fleeting moisture. These desperate meals are separated by agonizingly long intervals. The snail must gorge itself during a desperately narrow window, gathering every fraction of energy required to fund 100 days of suspended animation. Picture a brief winter rain passing over a rocky slope. Water darkens the limestone. Dust settles. Within hours, dormant snails soften their seals and push their tentacles into cool air. They descend from resting sites, feed across damp surfaces, seek mates, and replenish water. The landscape that appeared empty now carries slow-moving bodies under the night sky. The window may close quickly, a dry wind returns, shallow moisture disappears, and the ground hardens. The snail cannot negotiate with the weather. It must choose when to stop feeding and begin sealing itself again. Wait too long, and the journey to shelter consumes precious water. Stop too early, and it enters dormancy without enough reserves. That decision raises the stakes of our 100-day test. A healthy snail attached to a pale limestone slab may endure the interval. The same species caught on black stone, weakened by reproduction, or carrying too little water may die much sooner. Survival is not a magical number written into the animal. It is a balance sheet affected by temperature, humidity, body size, shell color, health, and the quality of the resting site. So if dormancy works so well, why not remain sealed all year? Because aestivation prevents death, it does not allow ordinary life. A dormant snail is not eating, growing, mating, or laying eggs. Its reserves continue to decline, however slowly. Damage accumulates. The seal can crack. A predator can find the shell. Time remains an enemy, only one moving at a reduced pace. Predators are especially dangerous because the motionless snail cannot flee. Rodents may gnaw shells for food or calcium. Birds can pick snails from exposed rocks and smash them against hard surfaces. Beetles and other invertebrates may attack vulnerable individuals. A shell displayed on a bare limestone slab is highly visible, so the thick calcium wall must serve as an impenetrable fortress. The seal itself can also attach the snail firmly to the surface. That prevents dry wind from rolling it away and reduces access around the shell opening. A snail fixed to a bare rock face may look carelessly exposed, but the pale stone can be cooler than the dark soil and less accessible to some ground predators. This extreme endurance raises a compelling question. If these defenses are so effective, could a desert snail survive far longer than 100 days? Under favorable conditions, some land snails can remain dormant for many months, and reports of exceptionally long dormancy stretch much further. But extreme claims need caution because inactivity is not always the same as continuous, experimentally verified survival without access to atmospheric moisture. Even a sealed snail may absorb or conserve tiny amounts of water under changing humidity. Cool nights can reduce evaporation. Morning dew may collect nearby. A pale rock face creates a different microclimate from the weather station several kilometers away. Calling the landscape dry does not mean the snail experiences identical dryness every minute. This is where the survival story becomes more precise. The snail does not defeat the entire desert. It utilizes the bare limestone where the rules are slightly less severe. Against the pale stone, away from heat-absorbing dark earth, temperature and humidity differ just enough to separate survival from death. At roughly 60 days, the animal may appear unchanged from the outside. The membrane still covers the opening. Dust coats the shell. Inside, however, its reserves are lower, and prolonged dormancy places stress on tissues. Protective molecules help stabilize proteins in cell membranes as water availability falls. Antioxidant defenses can also become important when metabolism changes and later accelerates during awakening. That awakening is more dangerous than it looks. When rain finally arrives, the snail cannot simply switch from near idle to full activity without preparation. Oxygen consumption rises. Dormant pathways restart. Waste must be processed, tissues rehydrated, and muscles powered after months of stillness. The return to ordinary metabolism can produce damaging reactive molecules, so the body's chemical defenses must be ready before movement begins. And the ultimate survival test happens at the sealed doorway. Rain strikes the shell and raises humidity around the epiphram. The membrane absorbs moisture and softens. The snail pushes from within, tearing open the barrier it built months earlier. Two upper tentacles emerge first, each carrying an eye at its tip. Then the foot spreads across the wet stone. It does not race toward a distant oasis. It begins with what the rain has placed within centimeters of its shelter. A film of water coats the rock. Dormant algae soften. Plant fragments release odor. The snail feeds and drinks through its body surfaces and mouth while the temperature remains low. If the rain lasts, it may travel farther, following chemical cues across the ground. It may encounter another snail, mate, or search for soil suitable for eggs. Every active hour now serves a deadline. The animal must repair the losses of dormancy before the desert closes again. So can a snail survive 100 days in the desert? Yes, if it is a desert-adapted species, enters dormancy with sufficient reserves, builds an effective seal, and attaches to a reflective limestone slab. It survives neither by toughness alone, nor by storing 100 days of drinking water. It survives by reducing the cost of being alive until the environment becomes usable again. The pale shell reflects sunlight. The trapped air slows heat transfer. The epiphram restricts evaporation. The metabolism drops, stored fuel is rationed, and the bare limestone slab keeps the animal away from the lethal heat of darker ground. Remove one defense, and the others must work harder. Remove several, and the sealed refuge becomes a tomb. That is the deeper lesson written across those dry limestone slopes. The desert does not always reward speed, strength, or aggression. Sometimes survival belongs to an animal smaller than a coin that knows exactly where to stop moving. Then, after 100 silent days, A few drops strike the rock. The seal breaks. A wet foot touches stone, and the desert snail begins again. If this survival story gave you a new respect for the smallest desert animals, click like. It helps more curious people find the video.